So this is the second video for this week. In this video I will give you a short introduction into MATLAB and the control systems toolbox. So the first time you open MATLAB, and I'm assuming that you already downloaded MATLAB and installed it. If not, I will leave a link that like the UCI page that shows you how to install MATLAB and download the license that UCI purchased for its students. So the first time you open MATLAB, you're going to be facing something similar to this. On the right here, you will have the workspace. The workspace is basically the place that shows us the variables that we have created and their values. The command window is a place where we can write simple MATLAB commands, like for example, if we write simple arithmetic operations like 1 plus 1, you get the answer immediately echoed into the command window. You can clear the command window with the command CLC. We can also create scripts, and for that you can, if you hit the button over here, control new script, or if you can just write Control N, that will open a new blank script. Here we can write MATLAB codes. For instance, we can just write CLC plus clear, and then we can create a variable called x, and let's put 4 in here, y, and put 5. Now I've just created two variables, x equal to 4 and y equal to 5, and then I can just create another variable and just add the two and store their value in Z. Now if I try to run this file by pressing either F5 or by hitting the button run here, I'll be requested to save it. For now, let me save it over here. This is test file. Now change the folder. If I run F5, as you can see, I have just run the file. Here you will see the three variables that I've created, x and y, and then z, which is basically the sum of these two values, which is 9. All right. We can also do other things than just simply adding or subtracting two numbers. And for instance, we can create vectors. In this case, let's make x capital to be vectors starting from 0 with a step of 0.01 up to 1. So when I run this file, I will have a new command additionally, which is the new variable x, right? And this variable consists of an array, right? An array of values that start at the element 0 and goes up to the element 1, right? As you can see, because I did not put a semicolon here, the answer was echoed back into the command line. I can put a semicolon and it will not be. If I still want to see the value, I can just write here x, and I will get the answer again echoed back into the command line. Now, suppose I want, for instance, to plot a simple function like the sine function, right? First of all, I have the variable x, right? And let me create y, and y will be equal to the sine of x, right? So the sine function is the sign that you know from calculus, the periodic function, right? And sine takes as input as either a single value or an array, and computes for each value in the array the corresponding sine function. So let me try to run this. Now if you have a look at y, it will be an array of values ranging from the sign of 0 up to the sign of 1. Right? Let us verify here in the command window that the sign of 1 is equal to the same value, which is at the end of the array, right? And the sign of 0 is equal to 0, which is the first value in our array. Okay, and in between, again, as you can verify it for yourself, sine function computes for each single value inside x the corresponding sign. Now suppose I want to plot this function over the range values from x starting at 0 and go to 1. I can just give it a new array, the two arrays, x and y, and if I run this file again, you will see that this is the range, that this is the function sine x between the two values from 0 to 1. Here, this is the x-axis represented by the x variable here, and this is the y-axis represented by the y variable here. Okay. Now let us try to make the range a little bit bigger so that we can see the full range of the function x. So let us start from 0, and instead of ending at 1, let us end at 2 times pi. Right, and you can verify that pi is the value that you're used to, which is 3.14, right? And we are moving at a step of 0.01. Now, if you run this again, you will see that this is the sine function that you're used to. All right. So as you can see, this plot command takes two inputs: the x points, right, and the y points, and plots, basically connects them with a line that goes through the points continuously. Right now, suppose I just want to plot the points themselves. I can use the command instead of plot. I can use scatter. Right? If you use the command scatter, you will see that the points are plotted instead of the line connecting them. So to make this clear, let us just use fewer points so that it's clear on the plot. Right? As you can see here, that the only points are plotted and no line connecting them. Now suppose I want to plot on top of that. I want to plot on top of this plot that I just did. Suppose I want to plot something else. Let's call it z, and z will be the cosine of x, right? And I want to plot this on top of the other one, right? So we can do that by using the command hold on. So hold on will keep whatever's going on here on this figure, right? And then we'll plot on top of it something else. In this case, let us plot scatter of x and z. Let us run this again. As you can see, we have the original plot, right? This is the original plot, the sine function, and then we have the cosine function, all right? Very well. There's a lot of functionality that you can add here. Either that you can, for instance, add a legend that help you identify. So we can just write this is sine of x. If I write here and then cosine of x, I run this command again, you will see here a small box here that that associates to each color on the plot the corresponding. Yeah, let me first clear the figure so that, yeah. So as you can see here, the small box here displays what plots are on the figure, right? And the first, which is the blue circles, right? The blue circles are associated to the sine function, and the red circles are associated to the cosine function. Also, we can add a title, right? We can add sine and cosine. You see the title here immediately appears, right? We can add x label. Okay. Let us say we can use for x the time so that x is our time, right? And then y label to be our how to say function value, right? And here you can see this is the function value, and this is the time, which is the independent variable and the dependent variable, and you can control the font of this. All of this can be found, and more options can be found in the help section, which you can access by going on the top right. You will see the search documentation search box, right? Here you can write just the word plot. If you write the word plot, you should get the help window to pop up. Here you will have MATLAB search database will give you everything related to the plot. In this case, we see the function plot here. And here we will see all the various variants of the function plot and the documentation of each option that can be used with the function. For instance, this is the example, the plotting of the sine function. This is the plot of sine and cosine, and so on. You have so many options. Now suppose we want to look up scatter instead. As you can see, here's the scatter function if you want to plot something, and so on. Okay. Now, so this is just a very basic introduction into MATLAB, and I will point you into more directions where you can find more exercises and more examples to familiarize yourself with MATLAB if you have not, if this is your first time to use MATLAB. For the purpose of this course, we will be dealing a lot with the control toolbox, right? So let me start a new file here. Start with CLC clear. Basically, the clear command, it clears the workspace, right? If you have any variables over there, they are cleared. And the CLF command, if you have any figures running and you run the CLF command, it will clear up the figure. Okay. Okay. So moving on, let us go to the control toolbox, right? Let us just search for here control toolbox, and we can see here that there's a lot of toolboxes up here, but we are interested particularly in the control system toolbox. This one we will be using extensively during this course, right? As you can see here, there's a lot of other toolboxes, but we just want to get started with the toolbox. All right. I encourage you guys to come over here and explore this, what is a linear system representation, basic models. Let us just, yeah. So we are basically interested in, or we will be using either transfer function models or ZPK, or zero pole gain models, right? We will be using these two functions a lot in our course. So let me teach you a small trick. We will be dealing with objects called transfer functions, and transfer functions, they encode the behavior of linear systems. Meaning that given a certain input, we apply the transfer function and we get the output. The output is basically the behavior of the system under the corresponding input. And the transfer function represents this this function, right? It represents how the system will behave with respect to each input. It's a way that encodes how the system will behave for each input. Okay. So and the basic object that we will be using is the complex variable S. All right. We will be working mainly in the complex domain. If you recall from your ordinary differential equation course, that S represents the like when you do the Laplace transform on a function on a differential equation, you get its corresponding Laplace transform equation, right, in the Laplace domain. For this, we can use the TF function, right? TF function will give us this. Okay. So now that we have created the variable S, we can start writing. Transfer functions. For instance, let us call the first transfer function G1 to be equal to 1 over 1 plus S. And this is a very simple function. It consists of a low-pass filter, right? If any of you took any signals class or have been exposed to this kind of terminology before, and don't worry, we will go over this in details during the course, but just to show you some of the capabilities of the toolbox. So so this G1 function, now we have a transfer function, and we can do a lot of things with a transfer function. For instance, we can compute its step response, and the step response is basically it is the response of the system corresponding to this transfer function due to a constant input of 1 that starts at time 0. Okay. So this function, when you give this the first input, when you give 1 a constant input of 1, you see that the system, you said that the step function will compute the step response and will plot it for you. Okay. You'll see that as time passes, this is the axis representing time, and this is the amplitude represents the amplitude of the output. Okay, so this is basically the output response in the time domain. Okay, like this is how the system behaves as time passes. Okay, so we can see that the system was initially at 0. And then it started ramping up due to the constant input of 1, and then as it goes on, we see that the system reaches the value of 1 eventually. It may not look like it here, but the system eventually reaches the value 1, right? Now suppose we want to know how much does it take for the system to reach the value 1, right? So let's say if you right click here inside the figure, okay, and we go to the characteristics option, you will see several timings here. First of all, you see the steady state. The steady state is basically the state or the output that the system will reach in basically infinite amount of time, right? Like how the system is going to behave when very long time have passed, right? So if we click on the steady state, you will see that a very small dot over here appears, right? And if you go there and hover on it, you will see that it says that the final value is equal to 1. Okay. Now suppose we want instead to look at the settling time. The settling time is basically, and it's a convention. It's the time taken by the system to be within a certain percentage of its final value. So if we click on settling time, you will see here the settling time to be 3.9 seconds. And this is basically the time it took the system to reach a certain percentage of its current value. And we can check the percentage here by clicking on the point, right? Let us just close, very close to it then. So this is roughly 0.981. So we can say that the settling time is basically the time it takes the system to be within, to be constantly within 2% error of its final value. Okay. Now the rise time is the time it takes the system to reach 0.9 of its final value. Okay, and there are, we will come back to this. Maybe my definitions are not as precise now, but we will come back to these, and these are called performance specifications. Okay. Another thing, if we look at the peak response is basically the highest value that the system achieves before reaching or before settling down. Okay. Because this is a very simple system, it's a so-called first-order system, and we will see what that means. The system does not overshoot. It does not go beyond its final value. It asymptotically reaches that value. Okay. Now, suppose instead we had a different function. Suppose we had G2, which was instead 1 over 1 plus s whole squared. Okay. Now this is a different function. Suppose we want to plot its step response. Okay. I'll just run this. So you can see the behavior of the system is different, right? Again, the system does not overshoot its final value. However, it takes longer time to reach that. As you can verify, if we look at the settling time, we see that the settling time is much longer than the other system, right? Took here about how much, like 5.8 seconds or something like that, right? And as you can see, if we look at the rise time, it took even more time for the system to rise to its final value. Now let us make things more interesting. Let us write something different here, like let us put this 5 and this s and this s squared. Okay. Now this is again a second order system. However, its behavior, as you will see, will be much different from the other one, right? As you can see here, we start to get some kind of an oscillatory behavior, right? The system does not, first of all, the system does not reach the required final value, right? Because our required final value is supposed to be 1, right? That's the input that we gave. We give a constant input of 1, and we expect our system to reach that constant input given an infinite amount of time, right? However, as you can see here, the system sort of settles down at a value that is much less than the constant input, which is 1, right? So let us look at the steady state here. We see that the steady state is 0.2, right? Which is much less, that's like 20% of the input of the system, right? If we look at the settling time, we can see that in this case it's even much bigger than the two systems that we had before, right? In this case it's about 7.56. which is basically, remember the definition of the settling time, right? Now, suppose that we look at the rise time, right? The rise time, we see here, it's much less than before, and this is because this is a second-order system, so it starts, initially it starts violently, right? And it even overshoots its steady-state value, right? It overshoots the steady-state value by having a peak over here. And we can verify that if we check the peak response, right? This peak response happens at a certain amplitude, right, and a certain overshoot. This overshoot is basically a percentage by which the system overshoots, or the response of the system overshoots its steady-state value, okay? Yeah, that's so this is the capabilities of the function step, right? This is the so-called step response, which is basically the response of the system due to a constant input of 1 applied at the initial time and then kept constant all the way to infinity, okay? Now, suppose we're not interested in that. Suppose we are interested in the so-called impulse, right, response. The impulse response represents the response of the system if you hit it at the initial time with a very big force, and then you just leave it to work out. And if you just hit it at the beginning time, and then if you hit it at the beginning time and then observe how the system behaves, okay? Now let us try to impulse this system, the second order system G2, and see how it goes. You see here that the system started from 0, right? And because there is no constant input, no persistent input, right? The input, we just hit the system at the beginning and then leave it and observe its response, right? You see that the system kind of oscillates around the value 0, right? And then eventually reaches it. So let us look here. We look at the peak response. That's the largest amplitude the system gets to before eventually settling down, right? And the settling time is around 8.1. Okay. Now suppose that we instead impulse G1. Okay. You see that the impulse response of G1 starts at 1, okay, then eventually reaches our desired value over here, the 0 response, right? Like if we look at the settling time, it's about 4 seconds, right? And the peak response is actually at the beginning. Now let us look on so-called unstable system. Let's call this G3. Okay, and G3 consists of the following. Now let us impulse G3. This is one instance of a so-called unstable system, and we will see why this is an unstable system later on. But for now, let us just check the impulse response. You can see here that the system starts initially from 0, right? But then as time passes, the system exponentially goes, the response of the system exponentially goes to infinity, right? This is the form of an unstable system, because what happened is that we initially, impulse response corresponds to an initial displacement, a very small initial displacement from the 0 initial condition. So if the system was quote-unquote stable, our system would stay close to 0, right? But instead we see that the system went very far from 0. You can hear that this is 6 to the times 10 to the power 25, which is very far, right? There's impulse and step functions have an interesting feature which we can give it the time which we are interested in. So for instance, we can just look at the first 5 seconds of the response, okay? Instead of leaving it open, okay? So you can see here that the system started from 0, right? And as time passes by the 5th second, the system has reached an output amplitude of 70, and it keeps going on, okay? So you can guess the system is probably unstable here, okay? Now let us try to add something more interesting. G4. G4 consists of 1 over 5 minus s plus s squared. And let us impulse this G4 system for 10 seconds. You can see here that the impulse response of the system started at 0, right? You can see that there is small oscillations, but these oscillations are growing, right? They are not dampening. And even if we make the time response, like if we make the time window bigger, let's say 100 seconds, right? You will see that the oscillations do not even don't get any smaller. In fact, they get bigger, right? Like if we try to zoom a little bit over here, you will see that if we zoom enough, because this is a very big number, right? This is like 10 to the power 16. Okay. Well, I mean, you get the picture, right? Like if we try to zoom a little bit here, you see that the oscillations keep on going. So this is another instance of an unstable system. Okay. Now, some of the tools that we will be using. So these are this is just an introduction to the function step and impulse, right? Another function that we will be using throughout the course is called the Bode function, the Bode diagram. And the Bode, when I write Bode of G1, okay, what I get is I will get 2 figures, okay? These 2 figures represent so-called the magnitude and the phase of this function, okay? And we will explain plenty about these 2, what they represent and what do we mean by phase and magnitude. But let me just give you a spoiler that the magnitude here, if you recall from my previous video, the radius in the polar or the exponential representation of a complex number, this is very related to that. This is the magnitude of the transfer function for different values of the frequency, which is loosely the values of the variable s in the complex domain. Okay. And then the phase is, again, if you go back to the polar representation, this is the angle that arises in the polar representation or the exponential representation. And this plot is plotted on the dB scale. Okay, if you remember dB, that's a unit for measuring noise, right? It's also used to measure the magnitude of signals, right? And this is a log scale. It's a log scale. It's not the traditional linear scale. So, for instance, this point corresponds to. Let me go back here. And so this point corresponds to frequency 3.5 rads, right? But if you go down here, you will see that this corresponds. It's between 10 to the power 0, which is 1. and 10 to the power 1, which is 10, right? And this is roughly 3.5, right? And the magnitude is negative 11.2 decibels, or dp, and we will see later on what this dp means. So this is one important function that we'll be using, and another function, which is the so-called Locus. Yeah, I wanted to experiment a little bit with this function. Like, for instance, let us check what the body diagram for G2 looks like. Okay, you see that if you remember, G2 was a second order system, right? You see this, there's a different kind of behavior here, different kind of phase behavior. What about G3, right? G3 was an unstable system, right? So you see here that the behavior is much different from the second order system that we had before. What about G4? Again, a different kind of behavior, right? So I just want you to experiment a little bit with these functions to familiarize yourself about what exactly they do. And the Locus function. Locus basically computes the so-called root locus of the transfer function. And we will come back to this later, but it basically shows how certain quantities known as the poles and zeros of the function behave under feedback. And of course, all of these terms will make sense when we come to this point. But for instance, so the function G1, if you go here, function G1 initially had at its denominator had only this quantity, right? And if you equate this quantity to 0, you will obtain that S will be equal to -1. S equal to -1 is the so-called pole of this transfer function. And as we do the root locus, we see that the function moves here, that this quantity, -1, starts at -1, and then moves to the left, right? It moves to the left. And this will make sense when we come to the root locus, but I just want you guys to know that about the function root locus, okay? Again, I encourage you to try to experiment with these, and I point out some resources you can have a look at. And also, there's one more thing I want to look at. Let's look at the root locus of G2, for instance. This is a second order system, so if you have a look at G2, you see that it has two poles here. Like when you equate this equal to 0 and you solve for the corresponding values, you see that it will be two complex values, two complex conjugate values, okay? These complex conjugate values are, like, this is a second order system, so it has two of these. These are called poles, complex conjugate poles, and they are in fact so-called stable, as we can see, because as we saw that G2 was a stable system, right? Because they lie on the left of the imaginary axis. Okay, and the root locus shows how these two poles behave under the feedback. Okay, the gain feedback, and we will see what this means later on. And yeah, that's it for today. Let me know if you have any questions. And so yeah, I don't really expect you to fully understand what I exposed to you today. All I was doing is I was just trying to get you familiar with some of the functionalities that we have. Now, I recommend that you explore the control toolbox over here. Like if you come over here to the search and go to the control system toolbox, I really encourage you to come here and explore this toolbox, see what functions they have, and so on, for your own good. Of course, we will cover them together at the right times throughout the class, but it would definitely do no harm, and in fact would be very useful if you could on your own come and explore this toolbox on your own. Also, there's an interesting features that MATLAB offers, especially for the control system toolbox. So if you go to the apps section, you will see that there are some interesting apps that the system provides, that MATLAB provides. For instance, the control system designer, this is a very, very useful tool that is provided inside the control system toolbox. And the linear system analyzer as well. PID tuner is one of the very the most successful stories of control systems is the PID, and PID is really it's the how to say, it's a universal go-to controller when you try to implement a certain industrial process. You definitely start with a PID tuner, and then you try to explore other options. But your first go-to controller is the PID tuner. Now, the control toolbox provides the PID tuner where you can tune the PID gains or however you like. Like, you change the gains and you observe the behavior of the system. And it even has an automatic tuner that gives you the best gains according to a specific criteria. And we will try to cover some of these tools, and we really won't be able to cover everything, but we will try as much to expose you to as much tools as possible. And yeah, that's it for this week. And thank you for your attention. Let me know if you have any questions. Stay safe.